Yeah, okay, that's fine. There's one other bugaboo that I always have to do. Anyway, the recording started, and it is August 4th. Holy crap, it's already August. This is the Western Automation Monday morning technical class, and we're going to talk about auxiliary components for drives, specifically two today, so that we can limit ourselves to the time allowed. We will talk about short circuit protection, code required. Things have changed with the code. Therefore, we need to understand those changes to properly specify short circuit protection. And we're going to talk about dynamic braking and regenerative braking on the motor side. And I'm going to start with the second subject. The definition of regenerative energy is when the motor becomes an alternator. And as I was saying before I started the recording, I use the term alternator for AC and generator for DC. Those terms are kind of used interchangeably. So understand that in this context, alternator, AC, generator, DC. The motor, the induction motor, becomes an alternator when the load drives the motor. And when the motor is driving the load, the motor is drawing current from the VFD and basically applying torque to the load. When the load is driving the motor, the load is applying torque on the motor is resisting that torque because of the frequency output from the VFD has a certain speed in the magnetic field, and the motor's rotor is overdriving that, causing the current to reverse and pushing power back to the VFD. And I'm going to share my screen. I always forget to include sound. Now let's use the screen. Okay, now, if we look at this diagram, tell me if you can see it.
Yes.
So this is a block diagram of the VFD and motor circuit with some filters and the gearbox and a load. The load here is a hoist. So it's a pure constant torque load. And it's the ideal application to talk about this sort of regenerative energy or energy flow in the system. When the load is being raised, we're pulling power from the line through the input filter to the VFD, through the VFD to the output filter, if there is one, to the motor, to the gearbox, and the gearbox applies a mechanical torque and lifts the load. When the load is lowering, that load, let's say it takes 100 kilowatts of power to raise the load, then when we lower the load, we're going to get 100 kilowatts back in our face. And I think you all remember that this front end of the VFD is a diode bridge for standard VFDs. I'm not talking about regen VFDs here. That diode bridge is a one-way valve. It allows power to flow from left to right, from the line through the drive to the motor. It does not allow power to flow back to the line from the VFD. Therefore, this is a wall in this discussion. When this motor starts to becomes an alternator and starts pushing power back to the VFD, we can't go back to the line with it unless we install regenerative equipment. So I got 100 kilowatts coming back to the gearbox. If the gearbox efficiency is 90%, I'm going to drop 10 kilowatts here. In this case, gentlemen, we have no ladies on, so ladies and gentlemen, I guess, just to be safe, poor efficiency works in our favor, to be honest with you, because I get to drop energy off. And especially in the discussion I'll have in a minute about flux braking, where we actually alter the motor's efficiency, it really works in our favor. So 100 kilowatts, back through the gearbox, I lose 10. Back through the motor, under its normal efficiency, I lose another 5. And then if I have a filter out here, it's typically 3% line reactor, I'm going to lose 3. So I've lost 18 kilowatts. I'm only putting 82 kilowatts back into the VFD. What do I do with that 82 kilowatts? Well, the standard method is to connect a resistor across the DC bus. So this is the DC bus of the drive. There's that one-way diode bridge. Here's the motor pumping 82 kilowatts back in through the flyback diodes, making DC. And here is where I want to focus you, the yellow portion of this circuit. Initially, when the motor becomes an alternator and pushes power back, it's pushing AC back, as I said. So when you measure here at T1, T2, 3, it's AC. These 6 diodes, similar to these 6 diodes, take the AC from the motor and rectify it back to DC on this DC bus. This is the plus rail of the DC bus. This is the minus rail of the DC bus. Initially, these power capacitors, which had been drained a little bit because the motor was lifting the load, have a little room in them to absorb some of that energy coming back, but not a lot. Now, the way that the drive protects itself from overvoltage, a little bit of a segue here, but please listen carefully. When the drive is a 480 volt input drive, this DC bus is going to run at a nominal 683 volts DC. When this motor is lifting the load, that DC bus is going to drop. It may go down as low as 600 volts. When the load starts going down, the motor becomes an alternator. We send AC back to T1, T2, T3. We rectify it through these 6 flyback diodes and start putting power back on the DC bus. That DC bus rises up through the nominal 683 and then keeps going, and will keep going as long as this load is being lowered. The drive will accept up to 820 volts DC before it overvoltage trips and shuts off this output bridge to protect itself. At approximately 730 volts DC, stand to be corrected on that number, the drive will start to fire this transistor right here. It's a switch. And if there is a resistor externally connected to this transistor, the 7th transistor, the dynamic braking transistor, it will shunt this resistor across the DC bus, and this resistor will start to absorb energy. So rather than letting the DC bus fly up to 820 volts and over voltage tripping, this transistor starts to fire and hopefully can send enough energy to the resistor bank to prevent the voltage from increasing to the overvoltage limit. Now, I'm going to correct something I said a moment ago. That switching doesn't start at 720, 730. It actually starts at 760 volts DC. My mistake was that the hysteresis, where we shut this transistor off, is around 720, 730 volts. So at 760 volts, motor regenerating, we start to send energy to the resistor. We shunt this resistor across the DC bus. It's a simple buoyant battery circuit. That resistor obviously has to be sized to handle the current and the wattage. And the way we size these resistors under hard loads, they're going to glow. That's okay. They're made for it. But now consider this. You want to mount this sucker where it's going to set something on fire. And typically on 10 horsepower and above, that means outside of the electrical enclosure. Some small servos in the 500 watt class, maybe 1,000 watts. That's even getting a little big. They'll have the resistor on the heatsink of the amplifier itself. A servo amplifier is nothing more than a fancy VFD. But be careful with that. Donald, I think I'm gonna. Okay. So I just muted the external noise there. So first we absorb with the capacitor, then we start to fire this transistor and push energy across the resistor, and that turns that energy into heat. How do we size this circuit? If I've got 82 kilowatts coming back at me, do I need an 82,000 watt or 80,000 watt resistor? Typically not. Because even in the worst case of this hoist where it's going all the time, I'm only going to get that energy back 50% of the time. Right? So that allows me to size the resistor bank for 40,000 watts. And that's a very heavy-duty resistor bank. By the way, if you have an application where you're actually regenerating more than 50%, actually, even if you are regenerating 50%, you really need to consider going to regenerative and not using dynamic braking. We'll talk about that a little bit in a second. Now, with regards to sizing, typically we look at how often we're going to regenerate on that typical application. A lot of applications are just to absorb the energy of the deceleration of the motor after the cycle is done, like on a conveyor or a centrifuge. And in that case, we can get away with about 10% of this energy coming back. So we're going to size this resistor for 8 kilowatts. When you go to the Yaskawa price book and you select a 10% duty resistor, that's basically how they've sized it. That's the most common sizing of dynamic braking resistors, mainly to absorb the energy of deceleration during the application or deceleration at the end of the application. When you start getting into these heavy regen applications, we need to look at much larger resistor banks, or we need to go to the next step, which is regen. We'll talk about that in a second. Now, hopefully you understand that this simple play of energy and how we dump it off. This is what a dynamic braking unit looks like if we're going to mount that transistor external to the drive. A lot of the smaller drives have this transistor internal. At Yaskawa, we always put the resistor outside away from the drive. However, in the larger drives, we actually have a separate dynamic braking unit. And it's a bigger capacity switch. We size them on amps. It's a pretty, it's an I equals E over R circuit because it's DC. So it's pretty easy to size how much amps are coming back at you. And if you ever need any help with that, drop me a note. I'll size it for you quickly. But the fact is that these external dynamic braking units are also sold by Yaskawa. Here are the part numbers for them. And they come in 4 different ranges. Those are basically somewhat nominally related to output current. And you can see we sell them in 4 different voltage classes. Here, the 400 volt class is our 480 volt in the United States. And basically, these dynamic braking units can handle switching 760 volts DC to a resistor bank. The resistor banks, we also sell them at Yaskawa. They are not manufactured by Yaskawa. You can buy them from Power Ohm. You can buy them from Post Glover. A whole bunch of people make resistors. They're just basically standard resistors. Now, how do you house those resistors? Well, at least in a NEMA 12 in an industrial environment, you don't want dust falling on them, not because you need to protect the resistors, but you need to protect yourself from igniting stuff. Outside, NEMA 3R is good for resistors. Don't ever put resistors in a closed box like a NEMA 4. I mean, for obvious reasons. So, That is the standard dynamic braking method. A dynamic braking transistor, either internal or external. In the larger drives above 150 horsepower, we don't put this transistor in the drive. So you'll need an external one. If you have a drive with an internal transistor, but your dynamic braking is higher than you think this can handle, you can still put an external dynamic braking transistor in there. You can still add this to the mix. And you're just going to basically not hook up this transistor. You're going to hook up the external transistor to the resistor bank. Now, what are the alternatives to that dynamic braking? Let me see here. Where's there it is. This is a very interesting product. This is called the R1000. And what the R1000 does is it basically takes the power. It's a dynamic braking transistor that doesn't shove the power back to a resistor bank like this one does. There's our CDBR braking unit traditional. There's our traditional resistor. Instead, the R1000 does connect to the DC bus of the AC drive, but it drives the power back into the line, therefore eliminating the resistors if you have a heat-sensitive situation. And it has some extra filters associated with it. It's a very interesting alternative, probably twice the cost of dynamic braking traditional, but effective when required. One other thing you need to know about this is that it's pretty much going to trash your power quality on the line, but only during regen. So probably not going to be a problem in complying to IEEE 519, especially since it's probably a small capacity relative to the total capacity of the power bus, but you need to be aware of that. The R1000 is a very effective tool when resistors are not allowed. Now, to regen, we have some regen alternatives, and I'm going to talk about the D1000 now. It's a product, looks like a VFD, gee. And the D1000 basically, if I can find a diagram here. All right, that's the basic D1000. This is the power on the left side. Let me see if I can. There's some filters that go with the D1000 to take out the PWM chop. This is the D1000 itself, and here's the VFD, and here's the motor. What the D1000 does is it bypasses the input diode bridge of the VFD, because that's a one-way valve. It connects directly to the DC bus of the drive. So what the D1000 and its associated filters are is a regulated DC power supply. Pretty cool. And when you look at the other products on the market that are regen, like the ABB ULH drives, Vacon's regen products, they package those as a complete unit. We do not. And there's a good reason why we don't. The D1000 gives you a whole lot of flexibility in a system. As a DC power supply to the VFD, bypassing the input diodes of the VFD, we could make this whole thing into one package. And from a marketing standpoint, that makes sense in certain single drive applications. But we're a technology company. We want to make maximum use of this module here. And because we basically are a DC power supply, this DC bus can be hooked up to multiple VFDs, as long as the total of the VFDs in power doesn't exceed the D1000. So let's say you've got a whole bunch of 5 horsepower hoists, and they're running some stage act or whatever, and at one point they all regen. Are you going to put separate 5 horsepower regen drives on all of those applications? That'll cost a fortune. Yaskawa's product allows you to put one D1000 in front of all those 5 horsepower drives. Let's say there's 10 of them, so we'll put a 50 horsepower regen drive out there. If there's 20 of them, we'll put a 100 horsepower regen drive out there. You get the idea. This is sized on horsepower, by the way. You can see that here. Probably a little small, but you can see that we size these things on horsepower. So you total up the horsepower of the drives you got, and you size the D1000. And you always buy it with its filtered package. So the D1000 is our regen solution. Can we do a 100 horsepower regen drive? Yeah, D1000 coupled up to the 100 horsepower VFD that you select. And then you have the equivalent of what the competitor calls their single module unit. We're just going to give you 2 modules. Can you use the D1000 with somebody else's VFD? Absolutely. You can mix and match VFDs on the output as long as they can accept DC bus input. By the way, there's a UL reg for that. Not all drives can accept DC bus input and maintain their UL rating. Be careful with that. A lot of the Chinese drives they overlooked getting that rating. So the D1000 has flexibility. That's our play in the regen world. When you want a single unit regen drive from Yaskawa, you go to the matrix drive. That's a completely different subject. We'll talk about that on another day. In my opinion, the Yaskawa matrix technology, U1000 is the model number, completely outclasses everybody else's regen solution. For a lot of reasons for that. We don't have time to go into that today. We will have a matrix class soon. So we've covered all of the ways that we can solve this little applications problem of taking energy back through the VFD and either putting it on the line with our regen solutions or with our CDBR resistor or R1000, basically wasting it off. Any questions on that? Okay, I'm going to ask you to hold with me a little bit over time today because it's important. The next subject is very important. I'm going to play a video from Steve Perot, one of my favorite product managers at Yaskawa, who recently retired, unfortunately. But this is an excellent treatment on the new rules associated with short circuit protection. And this is a very important point that you need to advise your customers on when they buy a VFD. So let me know if you can hear the sound or if you can't hear the sound. But this is Steve Perot's presentation on short circuit protection for VFDs, the new rules.
So first of all, there's this thing called available fault current. And this was introduced or cleared up in the 2020 edition of the National Electric Code. And it states that available fault current is the largest amount of current capable of being delivered at a point on the system during short circuit condition. And it's very important, the words in red there, at a point on the system. So let's remember that because a system generally would consist of a transformer somewhere, possibly going from medium voltage to low voltage. And obviously, the available short circuit or fault current right at the terminal of the transformers will be often very, very large. But at points further down the distribution system, that available fault current at a point in the system to which you would connect a load, such as a drive, that can be a lot different than the available fault current directly at the source. So let's all remember that, available fault current. So why should you care about it? First of all, electrical equipment has a wide range of ability to withstand that available fault current or energy resulting from. Okay, so improper selection and installation can result in extreme dangers such as arc flash events, even without opening an electrical panel. It can expel large amounts of energy that's deadly. the temperatures of this energy can be as high as 35,000 degrees, which is even hotter than the surface of the sun. It can throw projectiles, and it can cause normally grounded surfaces to become live. So how do you reduce the risk? By following the rules related to fault current. And the rules for fault current are established by the National Electric Codes, that being the NEC for the United States or the Canadian Electric Code for Canada. And it says that you must protect your branch circuit, which is typically the conductors up to the equipment. Now, this same protection, these devices, may often protect the equipment itself, but not always. And in cases where it doesn't actually protect the equipment, supplemental protection beyond what's protecting the wires is required. Okay, and then the equipment that's chosen, such as an electrical panel, needs to be chosen such that its withstand capability, or the short circuit current rating, is greater than or equal to the available fault current for the power that's connected to it. So as you can see on this panel here, the panel has a short circuit current rating of 14,000 amps. So obviously, if there was more available fault current at where the power is connecting to this panel would not be sufficient, or the available fault current would somehow have to be reduced. Another important point here, when installing equipment, you absolutely must follow the equipment instructions, which we'll get into some of these details. Okay, next, let's talk about some typical scenarios for protecting drives. First, what does a drive by itself actually protect? Well, it typically protects itself during overload conditions. It typically protects itself during output short circuit conditions, that is, a short between the drive and the motor. The drive will protect itself against that kind of a condition. And then in addition to that, it's protecting the motor, that is a single motor connected to its output. But what does a drive typically not protect? It typically does not protect itself from short circuits in its own DC bus. It also typically does not protect external conductors or multiple motors connected to a single drive. There are a few exceptions to that, because there are some specialty and large drives that include short circuit protection for DC bus. In other words, built-in fuses. And an example of this would be the Escawa U1000 matrix product. Another thing that happens to be going on with UL, which is a future thing and not yet a UL listed kind of situation, would be that they are considering the drive for being UL listed for protection of output conductors, but this is work in process. This is not available yet. So often, a separate device is typically required to completely protect the drive. And generically, we refer to those devices as overcurrent protective devices, for short, OCPD, which typically is a circuit breaker or a fuse. So let's look at a couple different drive protection scenarios. In the first case, we've got a feeder circuit that's feeding an overcurrent protective device that then is connected to the drive and to the motor. So in many cases, that overcurrent protective device is protecting the drive, and there's actually nothing else that's required. How do you know this? You know this by looking at the drive instructions and making sure that what's upstream is actually listed in the instructions for the drive. If it's not listed as UL protected device, then you have this other scenario that's going on where you have your overcurrent protective device that's protecting the conductors, but then you have to add, in order to completely protect the drive, an additional supplemental device. And again, in some cases that might be a breaker, but often when you have to add something, it's going to be fuses. Okay, so these are two sort of protection scenarios you can get into. Okay, so let's talk about this thing called short circuit current rating and amps interrupting capacity, because they are often confused. So a short circuit current rating is the maximum short circuit current a component or assembly can safely withstand. Okay, can safely withstand. These are very important words, and that's when protected by specific overcurrent protective devices. So the units that are normally associated with short circuit current rating are kiloamps or amps, never amps interrupting capacity, because again, these are applied to components or assemblies that are not the kind of devices that would open, such as a circuit breaker or a fuse. So SDCR is applicable to these kinds of devices. Okay, then we have amps interrupting capacity. So amps interrupting capacity is the maximum short circuit current that an overcurrent protective device itself can safely interrupt. So you see on the left-hand side, SCCR is safely withstand. On the right-hand side is safely interrupt. Okay, and the amps interrupting capacity units are typically an AIC or KIAIC. So again, on the left-hand side, when we talk about assemblies or components such as drives or terminal blocks, things that aren't meant to interrupt the current, those are expressed in KA. And on the right-hand side, these devices are expressed in AIC because they are interrupting devices. So hopefully that clears up that. Next, let's talk about a system such as the enclosure that we saw in the previous picture. Okay, if we have a system such as a drive and an overcurrent protective device, such as a breaker or a fuse, we can have situations where the ratings don't match. And this is often the case, most often the case. So let's take an example of a drive that has 100,000 amps SCCR, maximum capability, that has to be protected by something. Okay, and if we feed that with a circuit breaker or a fuse that has a 25,000 amps interrupting capacity, the combination of those two is limited to the weaker of the two. So that combination or that system would be limited to 25,000 amps, SCCR. Okay, let's kind of look at a situation where they equal each other. So both devices, the overcurrent protective device and the driver, both rated at 100,000 amps. In that case, the combination is actually rated at 100,000 amps. Now let's look at one where it's the opposite, where we have the overcurrent protective device that has an interrupting capability of 100,000 amps, but the drive only has a capability of 31,000 amps. In this case, the combination is 31,000 amps. So pretty easy to remember, right? It's just the lesser of the two rated devices. There are cases where there are combination ratings, okay, but we're not really discussing those today. Combination ratings for components, that is. Okay, let's next move on to the evolution of the UL standards and how that has impacted testing. So the evolution of the standards, let's talk a little bit about the background of that. So first of all, customers must follow instructions by installing approved OCPDs. Okay, I'm probably going to say that a number of times, but it's very important. And we also know that most customers want to use common, inexpensive devices. We all want to do that, right? But UL, in contrast, requires us and other drive manufacturers to do destructive testings And this testing has become more difficult in the past. And so what happens is the capabilities, the result is often different between drives that are exposed and drives that are enclosed. And I'll talk about why. So what does this mean for the future? Let's talk a little bit about in the past that the drive manufacturers worked very hard to provide customers with these very desirable and forgiving compatibility from these devices along with the UL listing. Now for existing product is grandfathered unless there are major changes to the product. But new product now, under the new UL testing requirements, has many limitations, this new product does, based on installation type and the required short circuit current rating that customers need. So let's talk about the changes. First of all, UL 508C has been around for a long time, as long as I've been in this business. But as of February 1st of this year, UL is no longer accepting any new applications for UL 508C. However, they are allowing existing projects to finish. So you will see a few manufacturers, including Yaskawa, that continue to release new product under UL 508C. Okay. Now, existing product that's already been out there for quite some time remains valid and does not need to be investigated to the new standard unless UL-related changes are made to the product. And generally, that means something very significant. Okay. So for a lot of product that's out there, UL 508C is absolutely fine, and there's no concern whatsoever in using product that's listed to UL 508C. And even under UL 508C, there is this thing called component breakdown testing. Okay, and it's very severe kind of testing. One thing we have to do is short the DC bus itself, which is the rectifier, which does cause an explosion by itself. And then also the more severe test is the shorted capacitor test. And previously, UL allowed drive manufacturers to submit a letter from a capacitor supplier to say that this kind of failure was not a failure mode. Okay. Somewhere in the last 10 years, I don't know exactly when it was, so I'm saying approximately 2015, UL revised the requirement that this test must now be performed in a letter from the capacitor supplier stating that it was not a failure mode was no longer sufficient. Okay, so even under UL 508C, in the last 5 to 10 years, the testing has become more severe. It's very important as we release new products, and that you may see some surprise differences between, say, for example, an A1000 and a G800. If they're both UL 508C, why did they have to have different rules for testing? That's because UL 508C evolved. Okay, so again, though, now the way of the future is really this new standard, which is 61800-5-1. That actually might look a little bit familiar to you, that number, because there is also a European IEC standard that that it's harmonized with. So you'll see an IEC standard with that number, and you'll see the UL standard, and they share a lot of the same requirements, but they are not exactly the same. So this was actually published all the way back in 2012. And we talk about component breakdown testing. Now, this component breakdown testing is even more challenging than 508C. Okay, even more challenging than the new requirement under 508C. And the biggest change there is that for products that desire to have a high FCCR rating, and I'll use the G800 as an example, which has a maximum rating of 100,000 amps. If we had tested that under 61800-5-1, we would have to take all of our products to a laboratory that was capable of supplying 100,000 amps and to use calibrated fuses. So it's gotten much more complicated under 61800-5-1. Okay, so let's talk a little bit about this component breakdown testing. As I mentioned before, we purposely cause shorts on the internals of the drive and see what happens with different kinds of devices, whether it be breakers, conventional fusing, or semiconductor fusing on the input, and we see what happens. So the test result greatly depends on the actual construction of the drive, the amount of fault current, the available fault current, and the type of input protection, as I mentioned. So when a drive is exposed to a customer environment, this is most difficult because we wrap the product or the enclosure with cotton, and essentially the pass-fail criteria, which I'm going to talk about in a little bit, is that the cotton cannot ignite. But before we talk about that, I want to talk just a little bit about a simplified power diagram for a drive to get us all on the same page. Many of you have seen this before, but we kind of can think of the drive in terms of three power sections, one being the rectifier section on the left-hand side, and this just changes fixed AC into DC, and the next section is the DC bus, and generally consists of a bunch of bus capacitors to store and filter the energy. And then the last section is chopping up the DC bus back into variable AC to control the motor. And we're going to focus our discussion for the moment just on that center section, on the DC bus section. Now, I'm showing a single capacitor there, but often there's multiple capacitors in series and parallel combinations. So let's talk about the shorted bus capacitor test. Now, normally on a 240 volt drive, the rectified value of that is nominally around 325 volts DC. So when we apply a short across that, as required by UL, the capacitor loves it. He says, I have 0 volts, I love it, no problem. Okay, now why is that? Because these are 400 volt rated capacitors. And certainly it has no issue with 325 volts, nor does it have an issue with 0 volts, right? But let's look at a 480 volt drive, and this would be the similar to actually a 600 volt drive too. Now keep in mind that the 480 volt drive is using those same 400 volt capacitors, but in series. So normally it would be sharing the voltage. So when we short one of the capacitors, and this is what we're required to do by UL, put a short across one of the capacitors. Again, that particular capacitor is very happy. Okay, but the capacitor that's connected in series to it doesn't like it at all, and the result is severe. Right? So again, 400 volt rated capacitors, you're applying 650 volts nominal typical DC to that capacitor, and it doesn't survive, and the event is severe. So let's discuss the component breakdown test just a little more. The test condition is such that we must surround the equipment under test with surgical cotton. When we're trying to determine the conditions for a drive by itself to pass the test, the cotton directly surrounds just the drive. But when we're trying to determine how the drive will pass when installed in a cabinet, the cotton surrounds the cabinet rather than the drive inside the cabinet. As we discussed on a previous slide, the purposely created internal short circuit is usually destructive. But destroying the drive does not mean it's a failed test. A test is considered a fail when the surrounding cotton ignites, when there is molten metal on the exterior, when a door or cover is blown off, when a ground connection is blown, or when a touch surface becomes live. Now this is most difficult to pass either when the drive is mounted standalone by itself or with its heatsink external for drives that have exposed capacitors. However, based on the type of overcurrent protective device used, we also have solutions that will pass for these installation conditions. The following chart summarizes the typical results from many common installation types with different overcurrent protective devices. On the left side of this chart, from top to bottom for both voltage classes, you'll notice 4 installation types. Those being completely enclosed, 2 cases of enclosed with external heatsink, and also standalone where the drives are completely exposed. Across the top from left to right, we have semiconductor fuses, which are the fastest acting and offer the best protection. In the next column, we have conventional fuses such as class C, C, J, or T, and these are also adequate protection in many cases. And then in the far right-hand column, we have molded case circuit breakers and RK fuses, which are the slowest acting devices and thus have more limitations of use. Now, based on what we have just learned about 240 volt drives, you'll notice there's only one case in which any of these devices won't protect a 240 volt drive. And that's the combination of a standalone drive with a circuit breaker or RK fuse. Even the 240 volt drive won't survive this because besides the shorted capacitor test, there's also a shorted rectifier test that won't pass for this combination. Now looking at the 480 volt and 600 volt cases, we can see there are a few more restrictions, and that's because of what happens when we do that shorted capacitor test.
I'll interrupt just for a second. It's 7:56. Those of you that have an obligation, this will run about 20 minutes over time. Apologize for that, but we had a lot of ground to cover on these two subjects. You're welcome to stay with me, and we'll run till about 8:20 today.
On the 480 volt and 600 volt class drives. Notice that for the case of external heatsink for drives with exposed capacitors, that's the yellow cell in the rightmost column, Yaskawa does not recommend circuit breakers or RK fuses for protection. That's because we know the test result would not be good. For the new GA800 and GA500, our instructions do not prohibit it, but we still do not recommend. In the future, you are likely to see more conditions of use and instructions, not only from Yaskawa, but also from many drive manufacturers. Another area I want to point out is the yellow cell at the bottom of this chart. In most cases, conventional fuses will protect a standalone drive. However, some large drives mounted in this way must be installed with semiconductor fuses, and Yaskawa has special kits available for these conditions. Okay, I know that's quite a bit to take in, but remember this presentation will be made available for your reference. Now, one more thing before moving on. Please note that this chart is only typical, and not only must you absolutely pay attention to product instructions for individual products, but also differences across models within a single product family. So let's talk about the summary of the UL impact. Well, customers must follow their drive product instructions, as we just mentioned, when using these devices to protect the drive. And UL requires that the manufacturers do destructive testing. The test result is greatly affected by the choice of these devices. Again, 508C has become much more challenging. New projects have to use the new standard going forward. And then capabilities are becoming different between exposed and enclosed applications. So this again is just a summary of what we just discussed. with regards to the UL standards. And another important point here on one of these previous bullets that I should mention is that we did mention that 508C products could be forced to get relisted to 5-1. And you also may see that Yaskawa pushes forward in getting what's presently listed as UL 508C, get them relisted to 5-1. Okay, so you may actually see that even though we are not absolutely required to do so. So anyways, to finish up with that, please pay attention to differences between products and individual drive ratings within a product. Okay, next let's talk about approved protection devices for the GA800 and GA500. And what those limitations are. So first of all, let's take a look at a couple different scenarios of enclosed versus exposed. And this is a little bit of review, but it puts it in perspective pictorially. So when a drive is not mounted in another enclosure, I'm calling that exposed. We can protect it with fuses, and the fuses that need to be used are listed in our instructions. So this is a thumbs up. This is okay. This is good. When we try to protect that exposed drive, not mounted in another closure with just a molded case circuit breaker, this does not work when it comes to something that needs to be UL listed. Okay, and does something need to be UL listed or not? Yes, it does. According to the NEC, it has to be listed with another agency. And then, of course, if it's listed, it has to be used per the instructions. So this kind of scenario no longer works. We actually were allowed to allow that to protect a number of drives in the past, such as A1000. Now, is the fundamental design of the A1000 much different than the GA800? It is not any different. It's just that the rules for releasing a product are different now than what they were when we released the A1000 10 years ago, even though both of these products are listed under and released under UL 508C. Okay, what about when drives are enclosed? Can we protect with fuses? And can we protect with circuit breakers? In most cases, the answer is yes, when the drive is mounted in the same enclosure. Conventional fuses, no problem. Semiconductor fuses, no problem. In most cases, molded case circuit breakers, no problem. How about when the drives are in the enclosure, but the overcurrent protective devices are somewhere else? The answer to that is yes also. These are both acceptable situations. However, there is an exception, and as I mentioned, as before, if we look at item number 2 there, when the fuses are actually semiconductor type, then they must actually be in the same enclosure. Okay. And the other thing that I had mentioned before is Yaskawa's position is that when a circuit breaker is protecting the drive, we want to see not only the drive, but the entire drive, including its backside, in the same enclosure if it has capacitors on the backside. Okay, so those are some exceptions.
I want to point out something here because a lot of customers do buy the drive and the NEMA 1 kit, which is the sheet metal that mounts below the drive in some of the larger VFD ratings, to achieve an IP20 or basically prevent people from touching the power conductors. And if you can see my cursor here, the NEMA 1 kit's typically located down below the drive because our input and output power conductors are located always on the bottom of the drive. Note that if you are mounting this thing not mounted in enclosure. Then where the heck are you going to put these fuses? Because item 2 says semiconductor type fuses must always be in the same enclosure as the drive. Therefore, note that if one of your customers is mounting this thing on the wall with the NEMA 1 kit, you can't use semiconductor fuses. There is no enclosure to put them in. Now, are you going to get dinged for that? Probably not. If you put these fuses in a little box right in front of the drive, that's probably going to be okay. But that's just a little anomaly that I'm pointing out for you.
Okay, now let's talk about some let's kind of show that a little bit more pictorially of limitations of enclosed G800. So just drives that are in another enclosure. The 240 volt situation is actually pretty easy because we have both fuses and circuit breakers when the drive is completely mounted in an enclosure. This is always a thumbs up, no problem. And for the 240 volts, even when the heatsink and capacitors are on the backside, this is no problem for the 240 volt drive. And I think if you think back to the prior explanation of those failure modes, remember that when we short the 240 volt capacitor, nothing bad happens. Or the capacitor on the 240 volt drive, that is. But when we move on to 480 volt, again, we have the drive mounted completely inside of the enclosure, and either fuses or a circuit breaker is absolutely acceptable. But then when we go on a 480 volt drive, and we apply fuses as the device, that's a thumbs up, that's good. But the circuit breaker, again, in the eyes of Yaskawa, and the same would apply for the 600 volt drive, is that we don't really like to see this as a protection method with heatsink external. Okay. Now the exception is that drives without exposed capacitors on the backside, and this is something that we will be clear about in our instructions as well. Those you could actually do this with no problem, and there Yaskawa would have no problem. If, as a matter of fact, we will make our cabinet designs this way ourselves, that if capacitors are not on the backside of the drive, if that's not part of the drive design, no problem in having the heatsink external, even when using a circuit breaker for protection. Okay, so with that said, both the GA800 and GA500 have very detailed information on what can be used to protect the drive in what situations. So the best place to find that, because when we released both products, that being the GA800 and GA500, during the development of the product and the finishing of the instructions, there was not time to get complete information into the instructions. And we do go through a user manual revision cycle that, since we're a Japanese company, Japan is involved with that, and it takes a little time. So what we've done in the meantime is create some supplements for both the GA800 and the GA500. So what I encourage everyone to do is, instead of going to the manual, please go to these supplements to get the most up-to-date information. Eventually, we will have this same information in the manuals. But for the time being, please use these supplements as your Bible, if you will, for knowing what can and cannot be used for drive short circuit protection. Okay. And here's an example of the GA800. You can see that we show the use of semiconductor fuses. We show the use of what I would call conventional fuses, being class CCJRT, and also the limitations associated with using a multi-case circuit breaker or an RK fuse, which you can kind of think of as the same. In all cases, the maximum SCCR rating of the GA800 is 100,000 amps, no problem. but there are conditions of use. In the case of a molded case circuit breaker, as I mentioned before, that can no longer be your means of protection for a drive that's not enclosed. And we make note of that in the manual. So please be aware of that. And then we also make note of the mention that when using semiconductor fuses, it actually has to be in the same box as the drive. And we've got a nice solution for that as well. If you really aren't wanting to mount a drive in an enclosure, a big drive. And then we also have a similar document for the GA500. It has slightly different limitations. First of all, the GA500 is limited to 31,000 amps maximum SCCR. So that's an important difference. And then as far as the MCCB style that needs to use, it's actually very specific right now in the case of the GA500. And the specific type of MCCB that needs to be used at this point in time is called a current limiting type. So please read the notes on that. We always suggest a current limiting type of circuit breaker, but in the case of the GA500, presently, that's what it needs to be. But we are doing additional testing to hopefully remove that restriction in the near future. Okay, so let's talk about the impact on our Type 1 kits for the G800. So first of all, as you may recall, if you're familiar with the G800, it goes to very large sizes up to 600 horsepower. Well, frames 10 and 11, 371 through 720 amps. Since the only thing that really can protect that drive in a standalone type of situation is a semiconductor fuses, we have made a special kit, a special Type 1 kit that actually is large enough to house semiconductor fuses. Okay, this is the only Type 1 kit that's available for these two frames of the 480 volt. And internally, it looks like this. It consists of the Type 1 sheet metal itself, plus some supports and bus bar for the fusing. Okay, now there's two actually, the customer must buy two separate things. That is, one is the kit itself that comes with the all the sheet metal parts and the supports and the bus bars. The fuses are purchased separately. So you can either purchase those from Yaskawa or from a third party. Okay, now let's talk quickly about the impact that this has had on the G800 packages. So I'm going to go through this pretty quickly because I do want to leave time for questions. But the G800 packages, which we released last November, is available in Type 1, 12, and 3R with a variety of options. Okay, in the cases of wall mount, some of these are heatsink internal, some heatsink external. In the cases of the floor mount, it's these are all external heatsink designs. So think about that for a minute, and maybe you'll think about what's coming next on future slides. So what we did is we wanted to prevent anyone from ordering only a circuit breaker to not be misleaded to think that that package was a protected package. So what we decided is that for any of those combinations with heatsink external, if you order a circuit breaker, you will automatically get fuses every single time for those particular combinations. Okay, so we make notes of this throughout our selection guide and throughout our price books. And I'm not going to ask you to study that now, but just be aware that in many cases, when ordering a circuit breaker, it automatically comes with fuses, and therefore you can't actually choose option F. Okay, it automatically includes it.
Now, you're also protected, if you will, when you price from the Quote Wizard. And this is a little short commercial for the Quote Wizard. It's one of our best software products. It's free download. And I would use it in lieu of the price books in all cases. It's automatically alerts you to any updates. So as long as you don't have the little blinking light in the lower right-hand corner on the quote wizard, you're getting up-to-date pricing. It allows you to put your proposal on your letterhead in a PDF and email it directly to your customer. It's probably the fastest way of getting pricing out. And it has these little protections in it to keep you from running afoul of the code.
Okay. Now this is not the case for 240 volt because we all went through the 240 volt scenario, but it is the case for 480 volt, and we highlight in our tables where this is the case, and it varies a little bit between type 112 and 3. It also varies between normal duty and heavy duty, so just please be aware of that. Okay. And in addition to that, we also tried to clear up so that because we are asking you to know what your available fault current is in the job you're trying to apply a package to. So we're helping you up front by listing for some very common combinations of our packages what the SCCR rating is, so that you can make your proper selection on the front end. And so either you would have to overshoot and say, I always need 100,000 amps because I don't know, but that will be forcing you into a more expensive package. So the best thing is to know what the customer's available fault current is and match it up with purchasing a equipment that has an SCCR rating that is adequate but not overkill. Okay, so we try to help you with that by making note of that in our documentation. So let's talk about the key points to our session. Now that that actually completes all of our related topics for today, but I want to leave you with the following takeaways, the following key points. First of all, the equipment short circuit rating selection is very important and should be selected based on, again, available fault current, knowing what the available fault current is. The second thing is most drives require a separate overcurrent protective device according to manufacturer's instructions and UL, of course. So please pay attention to instructions, and they are more detailed and more important than they were in the past. Next, UL approval has become much more rigorous, even prior to the new standard, changing the way drives can be applied, such as enclosed or not, which protection device is chosen, what's required for short circuit current ratio, voltage class, etc. Again, UL approval has become much more rigorous. UL 508C, again, those products remain valid indefinitely, and future products will be listed to the new standard, which a lot of us are just referring to as 5-1. And lastly, Yaskawa strives to provide highly reliable and safe solutions with clear, very clear documentation. Okay, great. We've completed our session.
Okay. Thank you so much for staying with me today. It was a lot of content to get through. Dynamic braking regen and short circuit protection for the VFDs are important subjects if we're selling VFDs and we want to be valuable technical resources to the customer. Again, thanks for staying over time. And it's 8:18, time to go to work. We'll see you next week. Have a great week. And thank you for attending the class.
Thank you.
All right, bye for now.